Hello everyone, my name is Neil Jackson and this is Lab 4 titled Circuits and Capacitors. So in this lab we were in charge of building multiple DC and RC circuits to analyze how they interact with their surroundings and the components within them. We used the node rule, loop rule, and different combinations of voltage laws in order to better understand the circuits. And once we get a firm grasp of how circuits work, it will greatly help us out in the real world because, circuits are everywhere you look. Knowledge of how circuits work and how to build them will 100% behoove you in the future. So in addition to writing everything out on the computer, I also wrote it out on a piece of paper. And as you can see, I have this is the first circuit we worked with, and I predicted roughly 0.2 amps. And then in the computer, I wound up getting that, lo and behold, the answer was 0.2 amps. So my prediction was fairly spot on. And then we moved on to some voltage predictions down here. And as you can see, the combined voltage from our two batteries was 3 volts. And then when I look at my calculated voltages and add them together, I wind up getting that my total voltage difference across my two resistors was 3 volts, which matches the battery, which is exactly what we wanted. And on the back, I have my current graph over here, which essentially depicts as we run into the batteries, my voltage will increase, and as I hit the resistors, they will go down. And in these steady segments of wire and the ammeter, voltage obviously does not move, so it just stays very constant. And I have that detailed in here, and then my calculations further support this over here. So here's a quick little picture of the 3 RC circuits we built in the lab. On the right, we have me charging the capacitor. On the left, we have the capacitor discharging and making the light bulb turn on. And on the right, we have the setup I used to read the voltage across the capacitor. And the results of the RC current is as follows. So as I was charging the capacitor, the bulb started off very, very bright. But as the capacitor started to suck away that charge and voltage, the current started to fall off and the bulb eventually turned off. And something very, very similar happened when it was just the capacitor and bulb. The capacitor was discharging, so the bulb started off bright, but as the capacitor lost charge, the bulb also lost brightness. All right, and then here's my times I got for my 10 ohm and 20 ohm on the charge and discharge. As you can see, when we add a higher resistance bulb, it takes longer to charge and discharge the capacitor, and both times are roughly the same. The lab then had us set up a battery, capacitor, and a 30 ohm bulb, and then monitor the voltage drop across the capacitor as it was discharging. We then had to plot this voltage versus time data, and then turn it to a natural logarithmic scale, where the slope of said linear line will be -1 over RC. And we knew to do this because the lab solved this beautiful differential equation for us and gave us exactly what the definition of RC was, which is the time constant, or the time it takes for the voltage and charge on capacitor to drop roughly 1 over E, that's about 36% of its original value. Here are the 2 voltage versus time graphs I came up with. On the left, we have an exponentially decreasing graph, which matches with the theories that we came up with in class. And on the right, it's what that same graph looks like with a trend line and in the natural logarithmic scale. And I wound up getting that the slope of this graph, or the -1 over RC of this graph, is equal to -0.3742. Finding RC, that gets us a value of about 2.6724 seconds. After calculating RC, I deduced that that's the time it takes to lose 36% of volts. More accurately, I should have 5.6890 volts after 2.6 seconds. Of course, that's my theoretical value, and then in reality, I have about 5.8 volts left instead of 5.6. And this 0.111 volt difference could simply be from an error in operating the online stopwatch. For our what if question, in reality, nothing has 0 resistance, meaning the ammeter will have some sort of voltage difference across it, which will be a slight skew of our data. For our why question, if we were to do just the battery and the capacitor, we're essentially taking away all current associated with the circuit. It's weird to say, but it's true when we look at it mathematically using the loop rule. So unfortunately, we live in a world where time is an intrinsic property of life, so this is only a theoretical thing. The capacitor won't be instantaneously charged, but instead it's probably going to blow up. And here are my results page with my RC value, my theoretical voltage left, and my actual volts left, and then a brief description of my error. Thank you very much for watching.